5.7, apply the fundamental theorem of algebra. All right. So I'm going to start with a little, like, not example, but example. So if we had x cubed minus 5x squared minus 8x plus 48 is equal to 0, and I'm going to tell you that that would factor into x plus 3 and x minus 4 squared. This has two distinct solutions, -3 and 4. I need some medicine out there. Because this one would be a repeated one. So this would just be the distinct solutions as -3 and 4. A repeated solution like, are they okay? Is a solution that gets counted more than once. So this problem actually has 3 solutions, -3, 4, and 4. But because 4 is a repeated one, it only has 2 distinct solutions. All right, so the fundamental theorem of algebra. The theorem itself says if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. The corollary to this theorem says if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x is equal to 0 has exactly n solutions, provided each solution that is repeated twice is counted as 2 solutions. And so on. So, like, if there was a solution that was repeated 3 times, we have to count it as 3 solutions, and so on and so forth. That's what that means.
Wait, what is it? N is greater than what? In the theorem.
Up here? 0. Oh. There. Now, all of this also implies that an nth degree polynomial function f has exactly n zeros. The number of solutions is equal to the highest power of x. So for example, if we had x to the fifth plus 3x cubed minus 2x plus 1, this would have 5 solutions. Next thing is the complex conjugates theorem. Which says if f is a polynomial function with real coefficients and a plus bi is an imaginary zero, of f, then a minus bi is also a zero of f. So if I had like 3 minus 2i was given to me as a zero, then I would also know that 3 plus 2i has to be a zero. And let's say there wasn't an a term, but I was given like 4i is a zero, then also negative 4i would have to be a zero. Similarly, we have an irrational conjugates theorem. So suppose f is a polynomial function with rational coefficients and a and b are rational numbers such that, I don't know if you've seen me use this notation before, but s dot t means such that the square root of b is irrational. So that'd be something like the square root of 2. If a plus the square root of b is a 0 of f, then a minus the square root of b is also a 0 of f. So the rule applies to complex numbers, and it also applies to irrational, like with the stuff in the radicals. That's the end of the notes.